How do you steer a 5,000-ton rocket? That's one of the biggest challenges SpaceX had to solve to fly one of the largest spacecraft ever built. For decades, rockets have relied on hydraulic systems to steer their engines, but SpaceX decided that wasn't good enough for Starship. Instead, they replaced them with electric motors. So, why would SpaceX move away from such a proven technology? Well, today we're going to explore how Starship's electric steering system works and why something seems such a simple change can give SpaceX incredibly precise control over its giant spacecraft. Now, before we begin, make sure to hit that subscribe button so you don't miss any more rocket deep dives like this. Thanks in advance, and let's get into it. Okay, first, let's clear one thing up. How does a rocket actually steer? Well, it's surprisingly simple. Imagine you're holding a powerful garden hose. If you point the stream straight down, nothing really happens except getting your shoes wet. But tilt it a little to the left, and suddenly you can feel the hose trying to shove you to the right. A rocket works exactly the same way. Instead of water, though, it's blasting out thousands of tons of superheated exhaust. And instead of your arms fighting the hose, it's the entire rocket changing direction. On Starship, the inner Raptor engines can actually swivel while they're firing. Engineers call this gimbaling, but really it's just a fancy way of saying the engines can point in slightly different directions. They don't move much, usually just a few degrees, but that's all they need. By pointing the engine slightly off-center, the thrust no longer pushes perfectly through the middle of the rocket. That creates a twisting force, or torque, causing the vehicle to rotate. Think of trying to push a shopping cart. If you push right in the middle, it rolls straight ahead, but push on one corner instead and the whole cart starts turning. Same force, completely different result. Starship works exactly like that, except the shopping cart weighs around 5,000 tons and is trying to leave the planet. For example, if the engines tilt just a few degrees to the left, the exhaust gets pushed left, which makes the rocket rotate to the right. It's just Newton's third law doing what it always does. Every action has an equal and opposite reaction. The flight computer is constantly making tiny adjustments like this, sometimes dozens of times every second. Most of them are so small you'd never notice, but together they keep the rocket flying exactly where it needs to go. And here's the interesting part. Rockets are actually designed to be a little unstable. That sounds a little bit insane, I know, but there's a good reason for it. A slightly unstable rocket can respond much faster to steering commands. The downside is that if you stop correcting it, it'll quickly wander off course, kind of like balancing a broomstick on your finger. Stop paying attention for 1 second, and gravity immediately reminds you who's in charge. Unlike airplanes, rockets can't rely on wings or tail fins once they climb high into the atmosphere. Up there, the air is simply too thin for aerodynamic surfaces to do much of anything. In space, they're basically just expensive decorations. So instead, the engines become the steering wheel. As long as they're firing, they can keep rotating the rocket by continuously changing where the thrust is pointing. Now, you probably figure out what the biggest catch is. The moment the engines shut down, thrust vector control stops working completely. No thrust means nothing to vector. At that point, the rocket has to rely on other systems. If it's still in the atmosphere, fins can help. If it's in space, small reaction control thrusters take over, firing tiny bursts of gas to keep the vehicle pointed in the right direction. Okay, so that's the basic idea. Honestly, it sounds pretty straightforward, right? You just point the engine slightly in the direction you want the rocket to turn, and physics does the rest. Except, there's one small problem. We're not talking about moving a flashlight or even a car engine. We're talking about moving one of the most powerful rocket engines ever built while it's producing hundreds of tons of thrust. A single sea-level Raptor 3 engine weighs about 1,525 kilograms, or roughly the weight of a small family car. You can't just grab it and give it a little nudge every time the rocket starts leaning. So instead, the engine is connected to two powerful actuators. Think of them as giant robotic arms. One actuator can extend while the other retracts, and by working together, they can tilt the engine in almost any direction. It looks surprisingly effortless, but those actuators are constantly wrestling with an engine that weighs over a ton while it's trying to launch an entire rocket into space. Not exactly a relaxing office job. Back on the early Starship prototypes, those actuators were hydraulic. If you've ever watched an excavator digging a hole or lifting massive chunks of concrete, you've already seen hydraulic systems at work. They use pressurized liquid to generate enormous amounts of force, which makes them perfect for moving really heavy things. A pump forces hydraulic fluid into a cylinder. The pressure pushes a piston, and that piston either extends or retracts. Since the piston is connected to the rocket engine, the engine tilts with it. It's a simple idea that's been around for decades, and it has an impressive track record. Hydraulic actuators help steer the Saturn V, the Space Shuttle, and countless other launch vehicles, so SpaceX wasn't exactly taking a gamble by using them. The downside is that all of that power comes with a lot of extra baggage. Hydraulic systems need pumps, hoses, valves, reservoirs, and hydraulic fluid, all of which add weight, require maintenance, and create more opportunities for something to fail. But perhaps the biggest drawback isn't the extra hardware, it's speed. A rocket is constantly trying to tip over. In fact, if you stopped steering it for even a moment, it wouldn't politely continue flying straight. It would very quickly remind everyone why gravity has such an impressive, undefeated record. To stop that from happening, Starship's flight computer constantly monitors the vehicle's position, checking it hundreds of times every second. The instant it detects even the slightest lean, it commands the actuators to tilt the engines, redirecting the thrust just enough to bring the rocket back into balance. A good way to picture this is by balancing a broom on the palm of your hand. The moment the broom starts falling to the left, you instinctively move your hand left to catch it. You don't pause to think about it, because if you do, the broom is already on the floor. A rocket works exactly the same way. The only difference is that instead of dropping a broom, you're dropping a vehicle worth hundreds of millions of dollars. The stakes are slightly higher. The problem is that hydraulic systems can't respond instantly. When the flight computer sends a steering command, a valve first has to open, hydraulic fluid has to flow through the pipes, pressure has to build inside the actuator, the piston has to begin moving, and only then does the engine actually start to tilt. Each of those steps happens incredibly quickly, but together they still introduce a small delay. Most of the time, that delay is tiny. But when you're making steering corrections hundreds of times every second, even tiny delays matter. That's one of the reasons SpaceX has been replacing hydraulic actuators with electric ones on newer versions of Starship. Instead of relying on pressurized oil, an electric motor directly drives the actuator. That means there are far fewer moving parts, no hydraulic fluid to leak, no pumps or hoses to maintain, less weight, and a much simpler system overall. It also has the potential to respond even faster, allowing the flight computer to make quicker and more precise steering corrections. And for SpaceX, switching to electric actuators makes a lot of sense. After all, this is a company that's closely tied to Tesla, which has spent years building incredibly powerful electric motors, batteries, and control systems. If anyone was going to replace old-school hydraulics with electric hardware, it was probably going to be them. In the current version, the Raptor engines have a gimbal range of roughly 15 degrees in any direction. And while that might not sound like much, it's actually one of the largest gimbal ranges you'll find on a rocket engine of this size. Remember, you don't need huge movements to steer a rocket. Even a few degrees is enough to redirect hundreds of tons of thrust, which is more than enough to rotate an entire launch vehicle. That extra range also gives Starship a lot more flexibility during some of its most demanding maneuvers. After stage separation, for example, the Super Heavy booster has to perform an incredibly aggressive flip before beginning its boost-back burn. Later, during landing, the engines need to make constant, precise adjustments to keep the vehicle balanced all the way down to the launch tower. A larger gimbal range gives the flight computer more authority to make those corrections, and moving the engine isn't nearly as easy as it sounds. Each Raptor 3 produces around 280 tons of thrust, or about 2.75 meganewtons. That's an unbelievable amount of force, and the actuators have to steer the engine while it's producing every bit of it. On top of that, they also have to deal with the spinning turbo pumps inside the engine. Those pumps rotate at tens of thousands of revolutions per minute, which creates gyroscopic forces that naturally resist changes in direction. Kind of like how it's much harder to tilt a spinning bicycle wheel than one that's standing still. So every time Starship changes direction, the actuators aren't just moving a heavy engine. They're fighting enormous thrust loads, the gyroscopic effects of incredibly fast spinning machinery, and the motion of an entire rocket that's accelerating through the atmosphere. It's a surprisingly demanding job for something that's basically acting like a pair of robotic arms. So, just by changing something that most people will never even notice, the actuators that move the engines, SpaceX isn't just making Starship a little better, they're making it a lot more capable. Better steering means the rocket wastes less propellant correcting its course, experiences less stress during flight, and can fly more precise trajectories from launch all the way to landing. Those improvements might sound small on their own, but they add up quickly when your goal isn't just to launch a rocket once, it's to launch it again and again and again. That's really the whole idea behind Starship. Instead of spending months refurbishing a vehicle after every mission, SpaceX wants something that's operated more like an airliner. Land, inspect it, refuel it, and send it back into space a short time later. Every improvement that makes the rocket easier to control or more reliable brings that goal one step closer. More precise steering also means better performance. If the rocket doesn't have to carry as much extra propellant just to compensate for uncertainty, more of its capacity can be dedicated to what actually matters: payload. That helps Starship move toward its goal of carrying well over 100 tons into low Earth orbit while remaining fully reusable. And that's only the beginning. Future Starships won't just launch satellites. They'll have to rendezvous with tanker vehicles in orbit, transfer propellant between spacecraft, land astronauts on the Moon, and eventually deliver both cargo and crews to Mars. Every one of those missions depends on extremely accurate vehicle control. Docking with another spacecraft, for example, isn't something you can do by eyeballing it and hoping for the best. When two vehicles are moving at nearly 28,000 kilometers per hour around Earth, even tiny steering errors can become very big problems. Landing on the Moon or Mars is just as demanding. There's no runway to aim for, no control tower giving instructions, and in the Moon's case, not even an atmosphere to help slow you down. The engines have to do almost all the work, so being able to precisely control where they point is absolutely essential for making a safe landing. It also adds another layer of safety. The more control authority the flight computer has, the better its chances of correcting unexpected situations before they become mission-ending failures. That's especially important for future crewed missions, where reliability isn't just nice to have, it's absolutely critical. And perhaps just as importantly, it gives SpaceX the confidence to keep pushing the limits. Every successful landing means engineers get the vehicle back, inspect what worked, fix what didn't, and use those lessons to improve the next version. That's been the company's philosophy from the very beginning: fly, learn, upgrade, and repeat. In fact, the switch to electric actuators is just one example of how much Starship has evolved. The new Raptor 3 engine has been heavily redesigned with a much cleaner layout, eliminating much of the external plumbing and heat shielding found on earlier versions. The engine is lighter, simpler, and easier to manufacture, while improved thermal management makes it more reliable during repeated flights. SpaceX has also redesigned the ignition system so the engines can start more quickly and more reliably, using pressure from the vehicle's own propellant tanks instead of relying on more complicated support hardware. That not only simplifies operations on the ground, but also improves the chances of successful engine relights in space. The plumbing throughout the vehicle has been cleaned up as well, allowing cryogenic propellants to flow more efficiently to the engines. Thanks to a redesigned central downcomer, all 33 Raptor engines on Super Heavy can now ignite at nearly the same time, producing a smoother and more coordinated startup than earlier versions. The booster itself has also received major upgrades. The hot staging ring, which was originally a separate structure, has now been integrated directly into the methane tank. That saves weight, reduces complexity, and makes one of Starship's most violent maneuvers, hot staging, even more reliable. Even the grid fins have been redesigned. Instead of 4 smaller fins with separate hardware for catching the booster, the latest Super Heavy uses 3 much larger grid fins that also double as the tower's catch points. Fewer parts, less weight, and fewer things that can break. It's a design philosophy that shows up almost everywhere on Starship, and that's really the theme behind all of these upgrades. They're not about making Starship look different. They're about making it simpler, lighter, more reliable, and easier to fly over and over again. Because without that, Starship is just another giant rocket. With it, SpaceX hopes it becomes something we've never really had before: a fully reusable spacecraft that launches like a rocket, lands with remarkable precision, gets refueled, and flies again. If they can pull that off, it won't just change how often we go to space, it could completely change what we're able to do once we get there. If you want to see another deep dive into how SpaceX is redesigning different parts of Starship, be sure to check out this video right here. I think you'll find it really interesting.